Hey guys, this is 7.3. We are going to practice simplifying radical expressions today. Thank you for watching. Okay, so we are going to break down radical expressions, multiply them, and divide them. So we're going to begin with what is called the product rule for radicals. Remember that product means what you get when you multiply. The product of 2 and 3 is 6, okay? So product rule means a rule for multiplication. If, hold on, it's always, all right, better. Okay, so this letter N is called the index or the root. The root of the radical or the index of the radical, okay? So if the index is the same, when you multiply the, let's just say like the square root of A times the square root of B, you can change that to the square root of A times B. So as long as the root is the same, we can keep that root and multiply everything that is under it, and then we can simplify it, okay? So remember that when we're talking about radicals, this one is an understood 2. So here the n is 2, the index is 2, the root is 2. So we call this the square root. The square root of 25 is 5. Do you remember why? Because 5 squared is 25, okay? So you can also put a different number here. You can put like a 3 here. And that would be, this was the square root. This is the cubed root or the third root. The third root of 8 is 2, because 2 times 2 times 2, or 2 to the third power, is 8, okay? And you can put whatever number you want here as the index. You can see anything as the index. We simplify by making a factor tree. So if I had the square root of 24, and I wanted to simplify it, I break it down into its factors. 24, I can divide it by 4, and I'll get 6, right? 4 is not prime. 4 can become 2 and 2. 6 can become 2 and 3, right? That's prime. Also remember, each row of your factor tree equals the top number in your factor tree. 2 times 2 times 2 times 3 is 24, right? So if I want to call this, if I want to simplify the square root of 24, because this is an understood 2, I'm looking for factors that are in groups of 2. So there are 2 2s here. So that means I can take a 2 out of that square root of 24. So I have 2 on the outside. Under the square root, I have the 2 times the 3, or the 6, right? So that becomes 2 square root of 6. The square root of 24 is simplified to 2 square root 6. You can always check that in your calculator. So that won't be a whole number, right? But if I put them next to each other, they'll both give me the same answer. All right, so we took a perfect square of 2 out of the radical. Now let's use the product rule to multiply and then simplify if we can, okay? Here we have a radical with a 3 underneath it. That is called the radicand. The radicand is 3, here the radicand is 5. So because these are both understood 2s, they have the same n, I can just multiply 3 times 5. I can put them together. 3 times 5 is 15. 15 is not prime, but it's also not going to simplify, right? So if I had 15, I could only break that down into 3 and 5, what it was before, right? And there are no pairs. So the square root of 15 is the square root of 3 times the square root of 5. And you can check that. The square root of 15, the square root of 3 times the square root of 5. Get the same. All right. The next example, again, it has the same index. This has an index of 3. This has an index of 2. Look over here, this is another index of 2. So the index of 3 is also called a cubed root. So the cubed root of 4 times the cubed root of 2, they have the same index, so they can be multiplied together. Don't forget to bring that 3 over. 4 times 2. So the cubed root of 4 times 2 is the cubed root of 8. And we know here that the cubed root of 8 is 2 because 2 to the third power is 8. Or, like I did 15 down here, I can do 8 down here. So 8 becomes 4 and 2. 4 becomes 2 and 2. 2 remains 2. So now I have 2 times 2 times 2. And because this is a 3, I need a group of 3. So those all 3 can come out. So the square root of 8 is 3 2s. Or sorry, the cubed root. That's my mistake. That's what I told you not to do. Don't forget the 3. The cubed root of 8 is 2 because there are 3 2s that make up 8. Multiplying 2 3 times gives us 8. All right, and here we have fractions. Don't worry, the rules don't change just because it's a fraction. The rules don't change just because it's a variable. Okay, so that's an index of 2. That means it's an understood 2 right here. So those are the same. They're both 2s. And we're just going to multiply straight across the fraction. So remember, we put everything under the radical together. 2 times b is just 2b. A times 3 is just 3a, right? So we have the square root of 2b over 3a. That's all we can do with that one. We can't simplify it because of the radicals. Or sorry, it's a radical. We can't simplify it because of the variables. You can't simplify the square root of 2 because 2 is prime. You can't simplify the square root of 3 because 3 is prime. And we don't know what a or b might be. Okay. All right, that should work. That should work for the rest of class. Fingers crossed. Now we have the quotient rule for radicals. Quotient is what you get when you divide. So this is a rule for division. The other one was the rule for multiplication. Okay. All right. If you have a fraction under a radical, you can split it into 2 radicals, basically, right? If the radical a and the radical b are real numbers and radical b is not 0, because remember, if you put 0 as the denominator, that is a undefined term. You can't find the answer to that. Good. So the root of a over b can be changed to the root of a over the root of b. Good. Here we have the square root, so that's an understood 2. The square root of 5 over 16. We're just going to simplify them if we can. So that can become the square root of 5 over the square root of 16. Why would we do this? Because it might be easier to find the square root of 16. We might be able to turn that into something, right? So let's look at 5. 5 is actually a prime number. So if I wanted to make a factor tree, I couldn't do anything. There's no 2 numbers except for 5 and 1. And if it's 5 and 1, that means it's prime, and you can just write it as 5. So I could write it just as well as like this, with a straight line with the 5. So 5 is just going to stay there. It cannot be simplified. But let's do 16. 16 becomes 4 and 4. I need pairs, and that's a pair. They can come out. Or you could say 16 is 8 and 2. 2 stays the same. 8 becomes 2 and 4, right? Now 2 is there. 2 is there. 4 becomes 2 and 2, right? So now I say 2 times 2 times 2 times 2 is 16. I want pairs. Here are 2 pairs of 2. Right? So now I can pull the square root of 16 is 2 times 2, which is 4. Either way, you do it like that, or you do it like that. Both of those factor trees are correct. So we got it into its simplest radical form. Over here we have 40 and 81. Let's do the same thing. We're going to change it to the square root of 40 over the square root of 81. Now, the square root of 81, you might just know, right? 81 is 9 times 9. That's a pair of 9s. So we say the square root of 81 is 9. What about 40? 40 can become 5 and 8, right? 8 becomes 4 and 2. 5 just stays 5. 4 becomes 2 and 2. 2 stays 2. 5 stays 5. 2 times 2 times 2 times 5 is 40. So I know that's okay. And I know it's prime because 2 is prime and 5 is prime. So I can take a pair of 2s, pull it out, and leave everything else in there, which can also be 2 square root 10. So the square root of 40 can be rewritten as 2 square root 10. We can check that. Let's do this first one. The square root of 5 over 16 is the same as the square root of 5 divided by 4. We get the same number. Good. Here, I have the square root of, and you can put it under the, under a fraction like this, under the radical like this, 40 over 81. Or you can just say 40 divided by 81. That'll give you the same answer. Is the same as 2 square root of 10 divided by 9. Or 2 square root of 10, 9. So we know those are correct. Checked our answers. All right, so we're going to use this quotient rule to simplify the following examples. Assume that all the variables represent positive real numbers. So we have the cubed root. So now I'm looking for groups of 3. The cubed root of 27 over the cubed root of 64, right? So let's look at 27. 27 I can divide by 3, right? If I divide 27 by 3, I get 9. 3 is a prime number, And then 9 can be divided into 2 more 3s. So 3 times 3 times 3 is 27. 3 to the third power is 27. The cubed root of 27 is 3. They are inverses of each other. So the cubed root of 27 becomes 3. The cubed root of 64 becomes 8 and 8. So there's 2, but we need 3. We need a group of 3, so it can't be 8. 8 becomes 4 and 2. 2 stays the same. It's a prime. 4 becomes 2 and 2. So now we have 2 times 2 times 2 times 2 times 2 times 2 is 64. Looking for groups of 3. I have 2 groups of 3. 2 2s that are groups of 3. 2 times 2 is 4. Or you could say 64. Not 8 and 8. We want 4. What's 64 divided by 4? It is 16. That makes sense because we're looking for 4s. 16 is 4 and 4. And the 4 is just 4. 4 times 4 times 4. That's a group of 3. So that comes out. So the cube root of 27 over the cube root of 64 is 3/4. Good. Now this is called the 5th root. There's no special term after cube. Squared, cubed, 4th, 5th, 6th, 7th. So this is the 5th root of 7 over 32x to the 5th. I'm going to rewrite it as the 5th root of 7 over the 5th root of 32x to the 5th. 7 is a prime number. There is nothing we can divide 7 by except 1, right? And we just get 7. So we leave that as the 5th root of 7. What about 32 though? 32, if we need 5, we can do a 4 and an 8. 4 becomes 2 and 2. 8 becomes 4 and 2. 4 becomes 2 and 2. Everything else stays the same. So now I have 2 times 2 times 2 times 2 times 2 is 32. I have 5 2s. So those just become 2. So the 5th root of 32 is 2. The 5th root of x to the 5th is just x, right? Do you remember that? Because we have 5 x's and we need 5 factors, a group of 5 factors. Or you can always take this number and divide it by this number. We get 1x. All right, example 4, we're just going to practice simplifying skills. We're putting it into simplest form, just like you did with fractions in a different math class, right? So like when you had 12 over 15 and somebody said, put it in simplest form, you could say, I can, 12 and 15 are both factors of, are both multiples of 3, right? So 12 divided by 3 is 4, and 15 divided by 3 is 5. So 12/15 is the same as 4/5. 12/15, 4/5. And even if you said 12/15 and then you asked it to put it into fraction form, it will simplify it for you into 4/5. Let's simplest terms. So that's what we're doing. So the square root of 40, we just need a pair of numbers. Good. So I can say 2 and 20, right? Now 2 will stay the same. 20 becomes 2 and 10. 2 stays the same. 10 becomes 2 and 5, right? Now those are all prime. 2 times 2 times 2 times 5 become 40. And I want to pull out any pairs. So here's a pair of 2, so that becomes 2. Everything else stays under. 2 square root 2 times 5 is 2, square root 10. Good. So the square root of 40 is 2 square root 10. Right here. Same index. It's an understood 2, so we're looking for pairs, okay? 300 can become what? Let's do 25. 300 divided by 25 is 12. 25 can become 5 and 5. 12 can become 3 and 4. 5 is prime. 3 is prime, and 4 becomes 2 and 2. So now I have a 5 coming out and a 2 coming out with a 3 left there under the radical. Good. 5 times 2 is 10. Square root 3. So the square root of 300 is the same as 10 square root 3. Square root of 15, I think we already saw this today, right? 15 becomes 5 times 3. Those are both prime and there are no pairs. So the square root of 15, we just leave as the square root of 15. The cubed root of 16. So because it's a cubed root, we're looking for 3 of the same number. So 16 is 4 times 4, but that's not my answer because it's not the square root of 16. So if it was the square root of 16, I could say that that's 4 because we're only looking for a pair. But this is the cubed root, so we keep going. 4 becomes 2 times 2. Now it's prime because 2 times 2 times 2 times 2 is 16, and I can't simplify 2 any further. Cubed means I'm looking for groups of 3. So this becomes 2. And then the last 2 I have to leave. So, yikes, don't forget that 3. So the cubed root of 16 is 2 times the cubed root of 2. The cubed root of 3 over 64. I can break that into the cubed root of 3 over the cubed root of 64. Now 3 is prime, so I'm just going to leave it. But 64, I might be able to break into groups of 3. We've seen this already in this class, 64, but we'll do it again. We'll do it a different way. Before we did 8 times 8. Now I'll do 4 and 16. 4 stays as 4. 16 is 4 times 4, and there are my 3. So the cubed root of 64 is 4. All right, so now we have the square root of x to the 7th. And remember, x to the 7th means that we just have 7 factors of x. 1, 2, 3, 4, 5, 6, 7, right? And because this is an understood 2, I want to put them into little groups of 2. 1, 2, 3. So I have 3 x's that can come out. And I leave that one underneath. So the square root of x to the 7th is the same as x to the 3rd times the square root of x. Good. Or you can always take this number and divide it by this number. So I'm going to take this number and I'm going to divide it by this number. And I get 3, right? With a remainder 1. So that 3 comes, the 3 come out and the 1 stays under. Good. Okay. Now we have the square root. Again, it's an understood 2. The square root of 20 over the square root of 16. Oh, sorry, x to the 16th. So 20 can become 5 and 4. 5 remains a 5. 4 can become a 2 times 2, right? Pull these out. So now I have 2 and the 5 stays under. Just like here, the x stayed under, here the 5 stays under. And the 2 comes out just like the 3 x's came out. So the square root of 20 is the same as 2 square root of 5. And then 16, remember we just divide 16 by 2, we get x to the 8th. We can make 8 groups of 2 out of 16. 16 divided by 2 is 8. Remainder 0. This was remainder 1, so we have 1x. This was remainder 0, so we have no x's under the radical. All right, use the quotient rule to divide. Simplify if possible. All variables represent positive real numbers. Okay, so here I have the square root of 20 divided by the square root of 5. Instead of, so here they're both under the same radical and I separated them to simplify it. Here they're under separate radicals, but if I put them under 1, I can divide 20 by 5, right? 20 divided by 5 is 4, right? And the square root of 4 is 2. Okay. Here we have 7 times the cubed root of 48y to the 4th over the cubed root of 2y. Good. Same here. 48 divided by 2, I could do that and I could change it to a simpler radicand. So here I have 48 y to the 4th over 2y. 48 divided by 2 becomes 24. Yikes, don't forget the 3. Don't forget the 7. 48 divided by 2 is 24. And then I have y to the 4th. And down here, I just have y. What can I do with y to the 4th divided by y? That also looks like so what I can do is I can cancel one of them out. I'll have nothing on the bottom or 1 on the bottom, and I'll have 3y on top. Or if you remember the properties or rules of exponents, when you're dividing, you can just subtract. So 4 minus 1 is 3. You're welcome to subtract. Okay, so I'm still not finished. I'll draw a line right here. So now I have 7, the cubed root of 24 y to the 3rd. 24. and I'm looking for groups of 3. So I know I can do 4 and 6 equals 24. 4 becomes 2 and 2, and 6 becomes 2 and 3, right? So here is my 2 that can come out, and then the 3 stays under the radical. Good, so that's my 24. And then my y to the third, remember we can either say 3 divided by 3 is 1, remainder 0, just like we did up here. 7 divided by 2, 3 divided by 3 is 1, remainder 0. Or I can say x to the third is x times x times x. And I'm looking for groups of 3. So that just becomes x. Oh, sorry, those are x's and it was a y. Pretend like those are y's. Y to the third. Y, y, y. Single y. So that means this becomes 7 times 2. We multiply the 2 times the 7 because they're both outside now. And then under the cubed root, we have the 3. And where does the y go? Inside or outside? We took it out, right? Because we divided 3 divided by 3 is 1, or we put it into a group. It is one group of y. So we have 7 times 2y to the cubed root of 3. 7 times 2 is 14 y times the cubed root of 3. There's my answer. All right, and that is the end. That is the end of 7.3. Thank you guys for watching and see you next time.